But we also have the other one that's called breathe first, and that's going to go to level by level, starting from the roots. That's the first level we have, or level 0, and then it's going to go to the level 1, and then go to level 2, and it's always going to print the elements level by level from left to the right. So again, I emphasize on left to the right. Even in here in the DFS, when I do in order, I go first left, middle, right. So first is going to be still left and then right. If I go post order, I go again, I go left, right, and middle. So left and right, it's like, still we first have the left. And if I do pre-order, I go middle, left, right. So no matter what, I always have left, right. I don't have right and then left, right? So that's just the, it's just I have to say the a rule, and or a preferences. We're always going to start with left, right? So let's do practice on the left order, in order, pre-order, or post-order. I'm going to go back to our simulator and just practice on those a little bit, and then we're going to start writing code, as I promised. What happened to my simulator? It's right here. So I'm going to clear this. I'm going to create our own tree. Or maybe just use the tree that we had in the slide, so the result's going to be similar again. So I'm going to add the same numbers again. So 60, 5,500, 45, 57, 67, 107, 59, and 101. So we have this tree, and now we're trying to, so you see all the traversers are here, but we're going to first do it ourselves, and so we're going to basically see what happens. So in order first. So we said when we do in order, let me see if I share this correctly before I go. Okay, so when we do in order, we have to first go to all the lefts all the way recursively. Then we go to all the middles, and then we go all the rights, right? So we're starting from root always, right? Binary search tree, always going to start in the roots. That's the head of your binary search link, list structure. And so you're going to 60, but you need to check if there is any left. Yes, we do have a left children, it's not null, so we go to 55. And we're going to do this recursively again for this new node. It's kind of like calling this again, right, in the left, and then we're checking the left does have any left child. This one does have a left child, so we go to the 45. Then we're checking the left side of the 45. Is there any left? No. So that's our left, so we're going to print out 45. And you can see that 45 is the smallest element in this list, really, in this binary search tree area. So then we have to do the middle. So that's why we print 45. And then we're going to the, to the right. And there's no right. So we're done with this. We revisit that. We're going to do backtrack. So, and the recursive algorithm is automatically going to do that. It's going to go to this one that doesn't have any left. It's going to go to middle of it, and then it's going to go to the right of it. And there's no right. So it's going to be out of a stack, so whoever was caller will go back to it. So we're going to go back to this one. Then 55, we already visit its left, so we're done with the left. Now we have to do the middle one. So 55 itself is going to be printed out. Then we're going to check in the right side. So we do have a right children, so we go to 57. But before, we have to check if 57 does have any left children. It doesn't. So we're printing the middle one, which basically the node itself, the 57. And we now have to check the right side of it. It does have a right, so we go to 59. We check the left side of the 59. There's nothing there. We print 59 itself. We go to the right side. There's nothing there. We start backtracking. We go 57. We did the left, right, middle of the 57. We go up 55. We finished. We visited all the children's and also this 55 itself. So we go back to 60. 60, we visited all of its left. So we have to do 60 itself. And now we have to check if 60 does have any right children. So 60 does have the right children. So 100. But before we do anything with 100, we have to check if it does have any left children. So 67, it doesn't have any left, so we print 67. We go to the right of it, there is no right, so we go back to 67. We visited 67 and all of its children, so we're back to 100. 100 doesn't have any left children anymore. We visited all of them, so we have to print out the 100 itself. Then we're going to the right side of it. So right side of it is 107, but before we even do anything with 107, we have to go to 101 because we do have left children. 101 doesn't have any left, so we print 101, doesn't have any right, we backtrack to 107. 107 doesn't have any more unvisited left children, so 107 is going to be printed out. It's going to check the right side. There is nothing in the right. We go back up 100. We check both children's. We go back to 60. We visited everything in this tree, so we're done. So in order is going to print 45, 51, 57, 45, 55, 57, 59, 60, 67, 100, 101, 107. So that's how the in order is going to print, and we can confirm that, right? So completely in a sorted order. It's going to sort it for us. Now let's do pre-order. So pre-order definition was what? So first in the pre-order, we have to go to the note itself. Then we go to the left side of it, and then we go to the right side of it. So that means we're starting from 60. We're first going to go to, I'm going to also write them down so we don't lose them. We started from 60. We print the 60 itself because we do pre-order. And then we have to go to the left side of it. It does have a left, so we go to 55. We print the 55 itself, and then we have to go to the left side of it. We do have a left, so we go to 45. We print the 45. We have to go to the left side of it. There is no left, so we have to go to the right side of it. There is no right. So we're done with 45. We visit all these children, so we go back to 55. 55, we need to go to the right of the 55, so 57. We print out the 57 itself, then we go to the left, there's no left, then we go to the right of 59 is going to be printed out, and then the left side of it, there's nothing in the left, then we go to the right, there's nothing in the right, so we're done with 59. We go back to 57, we're done with 57, we go back to 55, we're done with 55 too because we visited all of their children, so it's considered completely visited. So we go back to 60. 60, it's done with the left side of it. We have to go to the right side of it. So we go to 100. So we print the 100 out. We go to the left. So we print the 67 out. We go to the, sorry, I said right, left. We go to the left of the 67. There's nothing in the left of it. So we go to the right. There's nothing in the right of it. So we're done with 67. We visited. We go back up to 100. We did everything with the 100 as far as the left side. We have to go to the right side. So we go to the 107. We print the 107 out. And we go to the left side of it. So we go to 101 now. And we have to go to the left side of 101. There's nothing in the left. There's nothing in the right. We come back with 107. 107 doesn't have any rights as well. We visited completely 107 and all of its children. We go back to 100. 100, we're done with it. It's completely visited, and so we can go back to 60, and 60 also is visited. So we're done. So this is going to be the order that we expect to see in a pre-order: 60, 55, 45, 57, 59, 100, 67, 107, and 101. So let's see if we did it correctly. Yes, we started with 60. 55, 45, 57, 59, 100, 67, 107, and 101. So perfect. So we did it in pre-order correctly. The last one is going to be the post-order. So post-order definition is that we first going to do all the lefts. and then we're going to all the rights, and then we're going to go to the node itself. So that means we would start with 60, but we're not doing anything with 60. We go to the left, we go 55. We're not going to do anything with 55, we go to the left. So we go with 45. 45 has to check the left. So there's nothing in the left. So we go to the right. There's nothing in the right. So the only thing we have to do is print out the 45 itself and go back to 55. So we're done with the left side of the 55, but we have to now finish the right side of it. So we go to 57. For 57, we have to check the left. There's nothing in the left. We have to go to the right. 59, there's nothing in the left. There's nothing in the right. So we print out the 59 itself, and we go back to 57. 57, we did all the left and right children. We visit them. So 57 itself, and we go back to 55 itself. We go back to 60. So 60, we're done with the left side. Well, we're not done with the right side, so we go to 100. 100 has left, so we go to 67. 67 doesn't have any left or right, so we print 67, back to 100. 100 has to go to right side of it, so we go to 107. 107 has a left child, so we go 101. 101 doesn't have any left or right children, so what we do the print out with the 101, we go back to 107. So 107 doesn't have any right children. We did finish the left side, so now we're going to print 107 itself, and we're going to go back to 100. 100, we're done with left side and right side of it, so now turn, it's 100 turn itself, so we print it out, we go back to 60, and we're done with the left and right side of the 60 completely, so we're done. So it's completely opposite of the pre-order, as far as the fact that in the pre-order the root's going to be printed out first, but in the post-order actually the root's going to be printed out last. So we expect this to be printed out as 45, 59, 57, 55, 67, 101, 107, 100, and 60. So let's see if we did correctly, and we did correctly. Perfect. So now the last thing is left out for us is the BFS. Okay, to go level by level. So again, as I said, we go level by level, and always we're going to left for in each level, we're going from the left to the right. So in the root level, we only have one, so 60. We're going to print it out. Then we go to the next level. We only have 55 and 100 in this level. We have to do it from left to the right. So 55 is going to be first, and then we're going to print 100. And we go to the next level. So in the next level, we have 45, 57, 67, and 107. And that's the order we're going to print them out from left to the right. 45, 57, 67, 107. Then we're done with that level 2. We're going to the next level. In the last level, we have 59 and 101. And from the left to the right, we're printing them. So the order of the BFS should be 60, 55, 145, 57, 67, 107, 59, and 101. And it's not showing us in the basically animation, but we do have it on the slide. So I'm going to go back to the PowerPoint, so you can see the last one is showing you the BFS or BF traverse. Okay, so we're done with our traversing too. So we're going to do one more example of insertion, and we're going to start jumping into the coding. So this time, instead of having integers as a value, we have a strings as a value, right? So we have names, right? George, Adam, so on and so forth. So when we're trying to insert, sorry, this is for traversing. So we're trying to go over in order traverse. We're going to do the same thing. We're starting for the very left. So the very left, the most left is going to be Adam. So that's going to be the first one. Then we're going to go to all the rights. and all the middles and all the right. So Adam is going to be printed out. Then we'll go to Daniel. There, Daniel doesn't have any left or right. So we'll go back to George, and then we'll go to the right, and we're looking for the most left, which is going to be Jones. So Jones is going to be printed, and then we're going to back to the Michael. There's nothing in the left side of it. We go to Tom. We go to the left of Tom, Peter. Peter is going to be printed out. Then we'll go back up to Tom, and we're done. So that's in order. So we sorted it. And we can do the same thing, and you can see the results for post-order and pre-order. If I want to do it level by level or BFS, it's going to be George, Adam, Michael, Daniel, Jones, Tom, and Peter. So these are going to be the order for the pre-order. Sorry, BFS, right? So level by level from left to the right. So you see another example. The data, the elements, again, they're generic. They can be any type. And so when we start creating our binary search tree, we have to tell what is the type. So the next thing we're going to have to talk about it in the next video is going to be deleting elements from the binary search tree. This is the one that is a little bit hard because we have to consider all the different situation and possibilities, and when we're removing elements. So it's not like just we go ahead and remove something, because when we remove random nodes from this tree, then this tree no longer going to be a binary search tree if we don't do it in a systematic way. So we have to kind of move things around a little bit so it's become and maintain its properties. And so it's stay as a binary search tree. So the deleting has two parts, or two main cases, and for each case we have different scenarios. So we're going to go ahead and talk about it in the next video. So I'm not going to talk about the deleting right now. And then when we're done with the deleting as well, we're going to implement that one as well. But first, we're going to implement the search, the traversing, and the insertion. And then we're going to come and have a video that is going to talk about the deleting. We're going to implement the deleting as we're describing the different scenario of it, or basically. So I assume that we're going to have maybe another 2-3 videos just for covering this entire binary search tree. So at this moment, we're in this video we talk about the search, inserting into the binary search tree, and traversing. And also we talk about the basically the performance, right? In the best case, the search and the insertion, they're both going to give us the login. But the traversing, as you can assume, and you can see, it's going to be order of n, because we have to go through all the elements one by one and print them out. So we can't really go just to one branch. But we can do it in a different orders. And almost all of them, even all the possible DFS or BFS, they're all going to be kind of acting as a recursive algorithms. So there's a very important interview question usually about the binary search trees and how we implement, especially the traversing them in order, in pre-order, post-order, and also the BFS. How we're going to implement them. And we're going to do it together, but I want to emphasize that the DFS algorithms, most of the time, are going to be implemented in a recursive manner. And it's a lot easier, and it's like 3 lines of code, really. So it really makes sense to implement them in that manner. But sometimes, when you go to interview, they want you to, okay, you probably know how to implement that in a recursive way. And so what if you're going to tell us how we're going to implement it using another data structure? So if you want to implement that in a different types of data structure, you have to use a stack. So if implementing a DFS, we have to do backtracking, right? So backtracking as a best way to to implement that is going to be using a stack data structure. So we're going to implement the DFS algorithms with both stack and so maybe some part of it is going to be your homework. But just keep that in mind, that DFS algorithms most of the time are going to be implemented recursively, but you can also implement them with a stack. But as far as a BFS it's easier to implement it using Q. So we always implement it mainly with Q, but you can also implement it in a recursive manner as well, because that's kind of also a recursive mechanisms that you each time you go to its level and finding the children's of each, adding the children's of the previous level into the queue. So you basically know who are going to be the children from left to the right. So, and they're all going to be in the same level. We know that. So that is going to be implemented with Q. So if you don't want to implement them recursively, the BFS algorithm, if you want to implement it recursively, you have to use Q. So again, I emphasize the fact that the DFS is going to be the stack or recursions, and BFS is going to be Q or recursion. So you can see the basically another application of stack and queue, even to traversing a binary search tree. Okay, I'm going to stop the videos, this video here as well. Again, as I said, the video should not go over an hour, otherwise it's going to be too large for the Blackboard, so I keep them shorter. And take care until next video. And so next video for sure, we're going to first do the implementation. So we do have some coding in the next video. Take care. Bye-bye.